Analysis of first part of Joule's experiment gave us the general definition of change of energy as adiabatic work transfer across the boundary of the system. Now let us see what part 2 of Joule's experiment gives us. The procedure for part 2 of Joule's experiment is same as that of part 1, but the difference is that the copper vessel which is used in this experiment is not insulated. So the system is without insulation. So when I say system is without insulation, then there are chances of some other type of energy interaction rather than work transfer. Means we cannot say that only work transfer is crossing the boundary of the system. And that's why we can say that the system under consideration in part 2 is a non-adiabatic system, or I will call this as just any system. Now the remaining thing is same. The weight was dropped through same height, so this Z was kept same as before, and the experiment was repeated with different types of fluids, liquids, gases, etc., and the rise in the temperature was noted. But the observation was quite different. Joule observed that the rise of temperature in the second case was quite different than the rise of temperature when insulation was provided, means part 1 of the experiment. Now, if we want to achieve the same temperature rise as before, what we have to do? Correct. You have to drop the weight through different height to achieve the same temperature rise as before. Now, if height is different, suppose the height is now Z dash through which the weight is to drop to achieve the same temperature rise, then what is changing? The amount of work which is supplied to this non-adiabatic system is changing, which is equal to m into g into Z dash. So here the work transfer is changing. Previously it was m into g into z, now it must be m into g into z dash to achieve the same temperature as before, or same delta T I am writing. Now delta T is nothing but the change of state, because only one property we are measuring, and that's why for same change of state I can write as the amount of work required by the non-adiabatic system, means any system, is not equal to the amount of work required for adiabatic system. Previously it was m into g into z. Now for achieving the same change of state, means to achieve the same temperature rise, the amount of work required is different, that is m into g into z dash. Now this inequality sign has no meaning in mathematics. So we have to get rid of this. To get rid of this, what should be done? Correct. You have to add something of the same unit on the right hand side of the equation as that of the work transfer. And then we can think of this something. What this something could be. So again, by scientific intuition, we can say that this something is nothing but some other kind of interaction the system, rather non-adiabatic system, is doing with the surrounding. So rearrange this equation, we can write here W any is equal to W adiabatic plus some interaction by which the non-adiabatic system is interacting with the surrounding. Now let us give some name to this something. We will call this something as heat transfer and denote it by letter Q. So we have identified a new energy interaction other than work transfer with the help of part 2 of Joule's experiment, and we have called this other energy interaction the non-adiabatic system is doing with the surrounding as heat transfer, and the equation becomes WNE is equal to W adiabatic plus Q. By rearranging this equation, can say that Q is equal to WNE minus W adiabatic, and this is the correct definition of heat transfer. So heat transfer is defined as the difference between non-adiabatic work transfer and adiabatic work transfer. Note that while defining heat transfer, we have not mentioned temperature. So it is absolutely possible to define heat transfer without mentioning temperature at all. Now some students may think that we have measured the temperature with the help of the thermometer, and we have mentioned here the temperature rise in the procedure of this particular derivation. But let me tell you that this temperature is just used for fixing the initial state and final state of the system. You may use other property than temperature like pressure or any other measurable property to fix the initial state and final state, and you will get the same definition of heat transfer as the difference between adiabatic heat transfer and adiabatic work and non-adiabatic work. Now let us develop this equation further. In part 1 we have learned that this W adiabatic is nothing but negative of change of energy. So if you substitute for this as minus delta E and rearrange the equation, we get WNE is equal to minus delta E plus Q, and further rearrangement gives you the famous well-known equation which is already known to you, that is Q minus WNE is equal to delta E. So in this way the final equation can be derived. Remember, this equation number 2, Q minus W is equal to delta, is applicable to only closed system undergoing any process. The process may be any process, but the system must be closed. Because this equation is derived on the basis of Joule's experiment, and in the Joule's experiment, the system under consideration is a closed system. No mass transfer was allowed across the boundary of the system. So to summarize, part 1 of the Joule's experiment gives you the definition of change of energy of the system, and part 2 gives you two things. First, it defines heat transfer without mentioning the temperature and the general equation of first law of thermodynamics, which can be used for any process undergone by closed system. Now, this equation number 2 can be further expanded to encompass all the types of energy changes and all the types of work transfers. So that's what we are going to do next.